Today we are going to see Cameroon General Certificate of Education Board 2023 Mathematics session. That's question number 10 concerning curve sketching. So this solution is proposed by Science Modernizers and the question is displayed on the screen. So the question reads: a function f is defined by f of x is equal to x cubed divided by x plus 1 all of that squared. And so Roman 1 says state the domain of f, 1 mark. Roman 2 state the coordinates of the intercept of y equal to f of x. Roman 3 says find the asymptote of the curve y equal to f of x. Roman 4 find the stationary point of the curve y equal to f of x. Roman 5 find the intervals in which f is increasing and in which it is decreasing. Roman 6 find the point of inflection of y equal to f of x. Roman 7 draw a variation table for f, and Roman 8 sketch f. So let's get started with the video. Okay, so the very first thing we have is the function. So the function f of x, so we have the function f of x is given by x cubed divided by x plus 1 all of this squared. So that's the function. So the first thing is the domain. So let us begin by stating the domain of this function, Roman 1. So we are looking for the domain of f, domain df. So we defined in the previous video, in which the link is in the description, that the domain of a function are the set of possible values in which that function is defined. So for rational functions, we saw that for it to be defined, it will be defined for all values of x except the zeros of the denominator, since 1 and 0 does not exist. So it means we are going to exclude the points, the solutions of the point x plus 1, solving this equal to 0. Sorry, we are going to see that the domain of definition of this function will be all real values of x excluding the points where this denominator will be 0, and this denominator is 0 if and only if x is equal to -1. And so the domain of the function will be all real numbers, will be all x in the set of real numbers, such that x should be different from the point -1. So that's our domain. So the domain of the function, we can also write this in interval form. So in interval form, we are taking all real numbers and we are excluding the point 1, both from below and above, and then we get positive infinity. So this is the domain of the function in interval notation. So the second form, the second says state the coordinates of the intercept y equal to f of x. So Roman 2, here we are talking about the intercept. Intercepts. So we saw that there are two types of intercepts. We have the y-intercept. When does the y-intercept occur? The y-intercept occurs when x is equal to 0. So when x is equal to 0, we replace in our function. So if we let y to be the function x cubed divided by x plus 1 all of that square, which is our f of x, when x is 0, we clearly see y will be equal to 0 cubed divided by 0 plus 1 all of that square, which is going to be 0. So the y-intercept is 0. So we can write this intercept in the form of a point when x is 0, y is 0. Now the next is the x-intercept. The x-intercept. The x-intercept occurs when y is equal to 0. So when y is 0, we replace inside here. So what we get is we have 0 is equal to x cubed divided by x plus 1 all of that squared. So this is true if only if x cubed is equal to 0, and this means x should be equal to 0. So we have the x-intercept is equivalent to the y-intercept. So we have that the coordinate of the point of the x-intercept will be, we can write it in coordinate form, that will be 0, 0. So that's it about the intercept of the graph. Now we go to the Roman theory, which says we should find the asymptotes of the y of the curve y equal to f of x. So we have that's 3 marks. So let's find the asymptotes to that curve. That's the Roman theory. We are dealing with asymptotes. So we clearly saw in the previous video that we have 3 types of asymptotes. So let's begin with the first one. We have the vertical asymptote, and the vertical asymptote is we give the formal definition of a vertical asymptote, which is if the limit at the point does not exist, then that point is said to be a vertical asymptote. In other words, if it gives you infinity, that point is a vertical asymptote. But here our function f of x is a rational function, that's x cubed divided by x plus 1, all of that squared. So the vertical asymptote is simply obtained by equating the denominator to 0 and removing the point where it is not defined. So equating x plus 1, all of that squared to equal to 0. This is true if only if x is equal to -1. So that's our vertical asymptote. That's the equation of the vertical asymptote. Now the next is we actually have to understand that a curve cannot have both the horizontal and the slant asymptote at the same time. And so since the degree of the numerator, these are polynomial functions, since the degree of the numerator is greater than the degree on the denominator, we can observe that this curve does not have a horizontal asymptote, since evaluating the limit at infinity or plus or minus infinity will give us plus or minus infinity. So this curve does not have a horizontal asymptote. So let's actually verify that. So if you obtain the limit as x approaches, let's take the case of positive infinity of x cubed divided by x plus 1, all of that squared. So we see that this is the same as x cubed divided by x squared plus 2x plus 1. So in order for us to evaluate this, we divide top and bottom by the highest degree of x. So I will divide everywhere by x cubed. I will divide by x cubed, divide by x cubed, and I will divide by x cubed. So this simplifies and I get 1 divided by 1 on x plus 2 on x squared plus 1 all over x cubed. So we see that everything on the denominator actually approaches 0, because as x becomes so large, 1 on x goes to 0, 2 on x squared goes to 0, 1 on x cubed goes to 0, and so this goes to 0 from above. And so what we get here is the limit is positive infinity. So likewise from negative infinity we are going to have negative infinity, and so we have no horizontal asymptote. Now let's verify the case of the oblique asymptote. So for the slant asymptote, the oblique or slant asymptote. So for the slant asymptote, we saw the definition saying that we have that the slant asymptote is always of the form y is equal to mx plus c, where m is the limit as x approaches plus or minus infinity of f of x divided by x. So we are going to evaluate the limit as x approaches plus or minus infinity of the function f of x, which is x cubed divided by x plus 1 all squared times x. Now the degree up is just the same as the degree down, so we are going to compare the highest degree. So the highest degree below is x cubed and the highest degree above is x cubed, and if you evaluate this we get 1. So let us actually see how the 1 comes about. So this is just the same as the limit as x approaches plus or minus infinity of x cubed. So this expression is x squared plus 2x plus 1 times x. So we get x cubed plus 2x squared plus x. And so dividing top and bottom by the highest power of x, here we have x cubed, here we have x cubed, here we have x cubed, and here we have on x cubed. So this gives 1 divided by 1 plus 2 on x plus 1 on x squared. But as x approaches plus or minus infinity, this goes to 0, this goes to 0, and so we are left with 1 divided by 1, which gives 1. So what does it mean? It means that the value of m will be 1. Now the next thing we do is we get the value of c. So c is simply the limiting value as x approaches plus or minus infinity of f of x minus mx, of f of x minus mx. So this means we get the limit as x approaches plus or minus infinity. Our f of x is x cubed divided by x plus 1, all of that squared, minus m is 1x. So we simplify this expression and get the value of that limit. So this gives the limit as x approaches plus or minus infinity of, simplifying that expression, I'll take LCM, that will be x cubed minus, we'll have x times x plus 1 squared, that will be x into x plus 1, all of that squared. All of this is divided by x plus 1, all of this squared. So more simplifications, so we get, that's just the limit as x approaches plus or minus infinity of x cubed minus, if we open up that bracket, that this is x squared plus 2x plus 1, so if we multiply we have minus x cubed minus 2x squared minus x, all of this divided by, let me expand that, x squared plus 2x plus 1, so that's what we get. And so the term in x cubed cancels out this term and this term cancels out, and we are left with negative 2x squared minus x. So dividing top and bottom by x squared here to evaluate the limit at infinity, we divide by x squared, x squared, x squared. So what we are left with is the limit as x approaches plus or minus infinity of negative 2 minus 1 on x divided by 1 plus 2 on x plus 1 on x squared. So this gives negative 2. So at the end we get that c, therefore c is equal to negative 2. Now we can state the equation of the asymptote. So the equation of the asymptote y is equal to m, which is 1 x minus 2. So that's the equation of our slant asymptote. Okay, so now we have to find the stationary point. Okay, so the stationary point, we are going to begin by computing the derivative of the function. So that's Roman 4. We are talking about stationary points. So stationary points. So the first thing we do is I will let y to be the function x cubed divided by x plus 1, all of that squared. So let's obtain the derivative first. So dy on dx will be equal to, we're going to use the quotient rule. So we have the bottom constant x plus 1, all of that squared, and we differentiate the top, which gives us 3x squared minus top constant, which is x cubed, and we differentiate the bottom, it gives us 2x plus 2. all of this divided by the square of the bottom. That will be x plus 1 squared of that raised to the power 2, which will give us x plus 1 raised to the power 4. So if we simplify the derivative, we get this is 3x squared into x plus 1 all of that squared minus this gives I will factor out 2, that will be 2x cubed into x plus 1 all of this divided by x plus 1 all of that raised to the power 4. So x plus 1 is a common factor, so I'll factor out x plus 1 from these two expressions. I'll factor out x plus 1 and this x plus 1. So what will be left is we will have x plus 1 shall be a factor of everything that is left. Here I will have 3x squared into x plus 1, that will be left, minus here I will be left with 2x cubed. All of this is divided by x plus 1, all of that raised to the power 4. So we clearly see that this x plus 1 and one of these x plus 1s we cancel out, and expanding the numerator for further simplification, we will get 3x cubed plus 3x squared minus 2x cubed. All of this is divided by x plus 1 all of that cube, which gives us a final response of the derivative of the function to be x cubed plus 3x squared. All of this divided by x plus 1 all of that cube. So therefore dy on dx is equal to, let's write it down so we can write it, let it be more beautiful. So I can factor out x squared. What will be left inside will be x plus 3 divided by x plus 1 all of that cube, where x should be different from the point -1. So this is the derivative of our function. Okay, now for stationary points, at stationary points, the derivative of the function is 0. We have dy on dx is equal to 0. So this means I have x squared into x plus 3, x squared into x plus 3 divided by x plus 1 all of that cube is equal to 0. So let's solve for the zeros. So this means we have x squared into x plus 3 equal to 0. So either x squared is equal to 0 or x plus 3 is equal to 0, from where we get x is equal to 0 or x is equal to -3. So that is the x coordinate of the stationary point. Now if you replace this inside the y function, so replacing this value in y, so we have y, our function, let's get the y coordinates. Y will be, in the case of 0, when x is 0, let's begin, when x is 0, y gave us 0, so since it's the intercept. Now for x equal to -3, remember our function f of x is x cubed divided by x plus 1 all of that squared. So when x is -3, we get -3 all of that cube divided by -3 plus 1 all of that squared. So 3 cube gives 27, so we get -27 divided by -3 plus 1 is -2 all squared 4. So it means we have the stationary points will be the point 0, 0, and we also have the point negative 3, negative 27 divided by 4. So those are the stationary points of that curve. Okay, so now the Roman 5 says find the intervals in which f is increasing and in which it is decreasing Tk max. So here we are going to use the expression of the derivative that we obtained in Roman 4. So Roman 5, we are, in other words, in simple terms, we are studying the monotonicity of f. Okay, now it suffices for us to solve the inequality f prime of x greater than or equal to 0. Now f prime was already given, which we had in Roman 4 above, and f prime of x is given by x squared into x plus 3 divided by x plus 1, all of that cube. So we have to solve this greater than or equal to 0. So let's verify if that's the derivative. Yes, x squared into x plus 3, all of that divided by x plus 1 cube. So let's solve this inequality. So we obtain critical values. The critical values for the numerator, we have x squared equals 0 or x plus 3 is equal to 0, and for the denominator we have x plus 1, all of that squared is equal to 0. So this is true if on the numerator we have x is equal to 0 or x is equal to negative 3, and for the denominator we get x is equal to negative 1. Now these are the critical values of that inequality, and we know that this derivative is not defined at the point negative 1 as stated at this level. So we have to be very keen with this information. Okay, so let's proceed then and see. So I will present all of this on a number line. So this is my real number line. So I have the points. I will begin. Here is 0. Here I have the points. Let's see. I have let me shift this point. Here is 0. Here I have the point negative 1, and here I have the point negative 3. And so we observe the different regions that we have. So here I have the first region. I will put it down. I have region 1, I have region 2, I have region 3, and I have region 4. Now what we have is we are supposed to study the sign of this inequality. Now the point of the numerator, we can use dots to represent them, and that of the denominator we can use the rungs. Now for the monotonicity, since actually we don't need at the level of the monotonicity, what we need is the region where the function is negative. So what we are going to do here is we are going to verify which of these regions is positive or which of the regions is negative. And so if, for example, the region 1 is a region which satisfies or where it is positive, note that we are not going to include the point T itself, because including the point T here is a stationary point, so it cannot be included in the region where it is increasing. So let's get the respective signs. So we have negative 3 downwards. So if we take any value below negative 3 and we substitute inside this function, inside our derivative function, then we are going to get the sign. So if we take negative 4 for example and we substitute inside, we have negative 4, all of that squared, times we have negative 4 plus 3, all of this divided by negative 4 plus 1, all of that cube. So negative 4 squared is 16, and here we have times negative 1 divided by a negative number. So a negative number divided by a negative number will give us something positive. So it means that the first region 1 is positive. Let's use it with ink. So this region is positive. Now let's get the in between region 1, in between 1 and 3, that's region 2. We can take the value negative 2. If we plug negative 2 inside there, negative 2 squared gives 4, negative 2 plus 3 gives 1, divided by negative 2 plus 1 gives negative 1, all of that cube, which is negative. So the resultant sign here will be negative. In between negative 1 and 0, we can choose negative half. Substituting negative half, we have negative 0.5 squared, which will give something positive, so that's positive 0.25, then times negative 0.5 plus 3 divided by negative 0.5 plus 1, all of that cube. So this is positive, and that's a positive quantity, so the region is positive. And 0 and above, you can take any positive value, like 4, it will always be positive. Okay, so what we observe is, in between, in region 1, we have that the function is increasing, and in region 2, the function is decreasing. In region 3, the function is increasing, and in region 4, function is increasing. So what then do we realize? So this is actually the parity of the function. So we are going to see f is increasing. So let's write the range. F is increasing when x is strictly less than negative 3, or x is strictly greater than the point negative 1. So we are using the strict because it is all the regions excluding negative 3. At negative 3 itself, it is 0, and 0 means it is stationary. So in most cases, when studying the monotonicity, you can also solve the inequality sign f prime of x strictly greater than 0, so that you avoid the stationary point. But solving it, you have to have in mind, if you are using the bold inequality, that you have to exclude the bold sign or the stationary point. So this is the region where the function is increasing. Now the range of values, f is decreasing. F is decreasing when, so where do we see f decreasing? F is actually decreasing in between negative 3 and 1. So f is decreasing in between negative 3 and negative 1. So this is the range of value for which f is increasing, and that's the range of value for which f is decreasing. Okay, let's go to the next question. Okay, so Roman 6 is find the point of inflection of y equal to f of x. Okay, so now we are looking for the point of inflection. That's the Roman 6. So the inflection point. So what we observe is we have the point of inflection is actually we have to obtain the point of inflection. We solve the equation d2y on dx squared is equal to 0, but we know that dy on dx is equal to x squared into x plus 3, all of this divided by x plus 1, all of that cube, so the second derivative d2y on dx squared will be equal to, so let's write this in expanded form. So this will be equal to x cubed plus 3x squared, so it's divided by x plus 1, all of that cube. So differentiating this, we get bottom constant, we keep x plus 1 cube, sorry, we keep x plus 1 cube, and we differentiate the top, so it gives us 3x squared plus 6x minus the top constant x cubed plus 3x squared, and we differentiate the bottom. So this 3 comes down, so we have 3, we differentiate what is inside the bracket, that's x plus 1, we get 1, then we recopy the bracket x plus 1 to the power 3 minus 1, which is 2. So that's what we get, all of this divided by bottom squared. So the bottom squared will be x plus 1, all of that raised to the power 6. So let's simplify. Simplifying, x plus 1 is common, x plus 1 squared is common, so I'll take x plus 1, all of that squared is a factor of what's left here is we have 3 we have x squared plus 6x, there's x plus 1, so we have x plus 1 into 3x squared plus 6x, so that 3 we can factor out 3x, so I can keep 3x outside, 3x into x plus 1 into what will be left there will be x plus 2, so this will be minus x plus 1 all squared has come out from there, so I'm left with 3. I will factor out x squared into x plus 3. All of this is divided by x plus 1, all of that is to the power 6. So if I equate this expression to 0 for me to solve the stationary, the point of inflection, we get x plus 1, all of that squared, we have x plus 1 squared, we cancel with something here, and so here we will have 3x into x plus 1 into x plus 2 minus 3x squared into x plus 3 equal to 0. So let's solve the cubic equation. So this is equal to, this is x squared, expanding this we have 3x into we have 3x into x squared plus 3x plus 2 minus what we have the other way is 3x cubed minus 9x squared is equal to 0. So this gives 3x cubed. So we expand 3x cubed plus 9x squared plus 6x minus we have 3x cubed minus 9x squared is equal to 0. So we observe that 3x cubed and 3x cubed cancels, 9x squared and 9x squared cancels, so what we are left with is so there's an equation sign, so this means we have 6x is equal to 0, and this is true if x is equal to 0. So when x is equal to 0, we replace in y, we get the point 0, 0. So the point 0, 0 is a point of, okay, so Roman 7 says we should draw a variation table for f, that's 2 marks. So a variation table is a table which gives all the information about the curve, and the variation table actually describes how the curve is going to behave. And from actually this table, which we study the monotonicity of the function, that's already how the function should vary. So it means across our domain we should have such a variation. Okay, so let's draw that. That's Roman 7, I think. Yes, Roman 7 is the variation table. So we have VII. So the variation table. So here we have variation table. Okay. Now, to construct the variation table, we are going to take into consideration the domain, some asymptotes, and some critical points like turning points or stationary points. So I'm going to draw so my diagram is not straight, so we are going to draw a table lines are not straight, then you close this box. Okay, so here we have I will represent the domain somewhere above. I will represent the domain up. So I'm going to use another color line. We had our domain started from a point infinity. Then we had a point that we excluded. That was the point 1, which is -1 rather, in which that -1 is an asymptote. So I'll use the double lines to represent the asymptote. And sheet it as such, so that's our asymptote. So this is the point -1. Okay, then immediately after this we had infinity. So I will keep this positive infinity, I will keep this negative infinity. Now we had the turning point, our stationary point, which is the turning point occurred somewhere. We have it at -3 and -1. So I'm going to include the critical point -3. I'm going to include it inside here. So we have the point -3. So what we are going to do is we are going to study, I will just call this the sign of f prime, the sign of our derivative f prime of x. What is the sign of f prime? And here we'll call this the nature of f. Okay, so the nature means either you're increasing or you're decreasing. Now a way to set up the variation table is simply for you to evaluate limits at the bounds. The limit as x approaches -infinity of the function f. So remember, f is equal to x cubed divided by x plus 1, all of that squared. As x approaches positive infinity, this number below here will be positive, since any number squared will be positive, but negative, a number cubed will be negative. So it means as x approaches -infinity, our function is at negative, the limit is at -infinity. So at -infinity you can do this sort of a thing, and then at -3 itself you evaluate the limit at -3. So -3, if you substitute it inside here, we get -3 cubed is -27. That will be -27 divided by 4. So we see that in between infinity and -27 on 4, -27 on 4 is a value which is on the side, -27 divided by 4. So we clearly see that there is an increase. So it means it is increasing. It is increasing. Now, in other words, we can still use the signs. You simply choose any value in this interval and you are going to realize it is already somewhere on our monotonicity, at the level of the monotonicity. So in between -3 and -infinity, it is positive. So you simply come here and you put the positive sign. That's if you are using the table of sign. If you are using the method of limits, you proceed as you saw. Now if you evaluate the limit at 3 from above, it still gives you -3 on -27 on 4, and at -1 you evaluate it here. So here is -1 from below. -1 from below means we have something like -1.11111111. So if you substitute it here, 1 minus that will be negative, then this will be negative. So we have -infinity. So this will turn to -infinity at the level of below. So it's going to leave that big value and it's going to drop. Now using the table of signs, you will see that the sign was negative. So the sign actually is simpler. You simply use the monotonicity to deduce your variation table. It's something very simple. And so we now go to the next point, 1 from above. If you take 1 from above squared and 1 from above that, we are still going to have something negative. But the next stationary point which I forgot to include was the 0. We had the point 0. I forgot to include it. We had the point 0. Sorry for that. From here, yes, we had the point 0. So you clearly see that in between this point or this region at -1, what you still have negative infinity. Then negative infinity, we move up to the point 0. So at the point 0 we have we have 0. So from negative infinity to 0 you observe an increase, and from 0 to positive infinity, so here the sign is positive. So from 0 to positive infinity we do the same thing. 0 is 0, so here is 0, is 0, and here will be 0. Now to positive infinity, the limit as x approaches positive infinity of that function is positive infinity, so it means it is still increasing. So you see, the table of signs at the level of the monotonicity gives you already a variation table. So if you want to use signs, that's it actually, you simply use the sign. So but the simplest is to use signs to avoid problems at the level of computation of limits. So that's the variation table setup, and this already gives us the shape of the graph. Okay, so the last question says sketch the curve y equal to f of x. So in order for us to sketch the curve, we are going to use all the information that we had above, starting from the domain of definition of the function, and all these informations are represented on a table of variation. So the Cartesian plane is already represented as such, so that's the Cartesian plane. So some important points that we have to get is that this is the vertical asymptote, this is a slant asymptote, this is the point of inflection where this is where the graph changes its concavity. This is what we call a stationary point, in other words a turning point, and this is also the point of inflection. So rather, this is the intercept. Unfortunately, the intercept is the same thing as the point of inflection. So let us sketch that curve. So the first thing we'll do is we are going to represent our asymptotes. So the two asymptotes, we have -1. So we'll represent asymptotes with broken lines. Now, properties of asymptote that we have to note is that an asymptote in itself, a curve does not cross an asymptote. Especially, a curve does not cross a vertical asymptote, but a curve can cross the slant asymptote or the horizontal asymptote. Now we have the slant asymptote y is equal to x minus 2. Now for us to easily sketch this line, we begin by getting the two intercepts for the line. When x is 0, y is -2. So I come somewhere here and I present my -2 when x is 0. Now when y is 0, we have 0 is equal to x minus 2. This means x is equal to 2. So I represent the point x is equal to 2 somewhere here. And so I now link the 2 points with a broken line since it is an asymptote. So that's a slant asymptote. So it goes like that right up to infinity. So sorry if the line is not straight. And also one thing we have to notice, the point of intersection of this asymptote, of these two asymptotes, is what we call the point of symmetry of our curve. So it was naturally asked in the question. Now, with all this, curves can cross horizontal asymptotes and vertical asymptotes, but curves cannot cross a vertical asymptote, only horizontal and slant asymptotes, but they can never cross the vertical asymptotes since they are not defined at that point. Now let's represent our points gradually. So let us begin with the point, our intercept. So the intercept is 0, 0, so that's the point, and this intercept is the same as the point of inflection. Now let us represent the first stationary point, which is our turning point, which is the point where the graph changes the slope. So we see from -infinity to 3 on our variation table that it is increasing, and from 3 to -1 the graph is decreasing. So it means there is a change of slope it is in this manner. Sorry about that. Okay, so there is a change of slope, something like this. Okay, so that's the same thing that is going to occur here. Now we have to plot the points negative 3, negative 27 and 4. Negative 3. Now when you take the point negative 27 and 4, negative 27 and 4 in decimal points will give us 6.75. So it means we have negative 6.75. That's negative 27 and 4, which is about negative 6.75. So it means the point will be found somewhere inside here. So that will be our point. So apart from that, there is another point for us to represent. Okay, so let me erase this so that we now sketch the curve using that information. Now, as I said, the variation table gives you tangible information about all those things. Now we begin from negative infinity to negative 3. The graph is increasing, so it means you are leaving from a small value ascending to a bigger value. So I am leaving negative infinity. I am leaving negative infinity, coming upwards, and when I reach this point, I turn and I slope back downwards, but I will never touch this asymptote. I will never touch the asymptote, so the line continues, so on and so forth. So that's the first part of the curve. Now the second part of the curve is from negative 3, from negative 1 we observe an asymptote right up to positive infinity. The graph increases, but at the point 0, 0 is a point of inflection, so we have to note that it changes its concavity at that point. So we are going to begin our graph. So at this point the graph is increasing, so it increases right up to positive infinity. Now remember, a graph can cut the slant asymptote. So what we have is, it's going to change its concavity. It's quite unfortunate that it's going to change its concavity, and the graph will increase upwards right up to positive infinity. So that's the nature of the graph. So that's definitely how the shape of the graph will be. Okay, so this is the typical shape of the graph as seen. Quite interesting. So the graph goes on like that throughout all of its domain, and at the point of inflection, so the change in concavity, it's somehow seems something like this, then it goes like this. Okay, so let's get a view of this on GeoGebra. That's a powerful mathematics tool. Let's get a view of this curve on GeoGebra so that we see all these points keenly. But the only thing is, GeoGebra will not actually define you these asymptotes. It's not possible, but we are going to sketch all those. Okay, let's use GeoGebra and you see what we can have. So this is the GeoGebra platform, or GeoGebra. This is just how the entry icon is. So let's insert our function. So we have x cubed divided by x plus 1, all of that squared. So clearly we are already observing the nature of our graph. So we can zoom out to see some things. So this is the point of inflection here. That's the point of inflection. So the point 0, 0. It's at the point 0, 0. So I'm just going to represent the point. I'm just going to place a point there. The point 0, 0 itself. Okay, so that's our point of inflection. So we clearly see how it actually changes slope. It changes its slope concave upwards. Then you see it being, so you see it actually changing its slope and being concave upwards. Then it changes stationary, then it goes back up. Okay, so that's something very important that we actually have to note. Then now what we observe again is, so let's erase this. Okay, so let's go to the turning points. So our stationary points, or the points where the graph changed the slope, was the point 3, negative 3. Let's point that, comma, negative 3, comma, negative 7, no, negative 6.75. So that was the point. So it is denoted here. Here is the point that has appeared. So this is the point here. So it's called point B. Now this is actually the turning point. So as you can see, that's the nature of the graph. So if we were to see, since the slant asymptote is not displayed, we can draw the slant asymptote. That's y is equal to x minus 2. So you clearly see how the graph cuts the slant asymptote. So that's it. It is split. And also we can also draw the line x is equal to negative 1, x is equal to negative 1. So you clearly see them. So let's go to the properties of these lines and make them like asymptotes actually. So since asymptotes are not represented with both lines, let's use lines, and also let's try and change the color. So let's use a sort of a color for that, and for this let's use a nice color like let's see, is green making sense? Okay, let me take darker one. Okay, then let's also change the color of our curve. I like blue. Okay, so that's a typical graph. So you see that this graph will keep on approaching these values, but it will never touch. So this is the asymptote. So let me remove that label. Okay, so it's the same thing. So this is exactly the curve that we had. This is exactly the curve that we had above here, as you can see. So all the properties here are actually met. So that's how we can actually sketch a curve. And I hope that the video was helpful. So if you loved the video, please do not forget to like, to click on the subscribe button for more updates. See you in our next video, and thanks for watching.